about the actual equation of the gradient descent algorithm. Okay, so for the gradient descent algorithm, before we talk about the equation, we should talk about the learning rate. So I have already said that when you go down the mountain, you go in the direction of the steepest slope. But there is a problem when you go down the steepest slope, that you keep moving very fast. Okay, and then you might miss the lowest point, the minima, and then shoot up on the other side. Okay, like exactly in this case where you might go from here and then go up here. Okay, so when you this is the direction where the gradient is descending or lower, the negative. But when you meet here, gradient becomes 0, and then again gradient goes up. Okay, with the change increase in the value of x. You don't want to go that direction, so we have to be very careful when we do that. So what we do when we go down the steepest slope, to minimize the time or to reach the bottom or to minimize the convergence time, at the same time we have to keep a control on our feet and kind of braking, so that we do not overshoot that point where we want to actually land. This factor which kind of breaks your speed or controls your speed is called a learning rate. Okay, this is like a fraction, and it is multiplied with the derivative when you are going down, so that it kind of give you a break, and so that you can finally converge without overshooting. Now, if your brake is very kind of good, then you will definitely reach to the bottom of the mountain in kind of minimum time, because you are going in the direction of the maximum slope or the highest slope. But so that is called good step sizes. Okay, converges quickly. That means you go down and hit the bottom exactly where you want to go. But if the step sizes are large, that means, oh my god, I'm going too fast and the brake is not good. What can happen, I can kind of jump from this side to that side, and but finally is not being able to hit that. Okay, so you increase the x, it's so high that it comes to that side of the gorge, and then again to this side. It's like a glider going from this side to that side, but not being able to land in the bottom of the this chasm or whatever you call it. But now but if what happened, you are too scared, and you are giving very high brake and taking very small steps, then going down to the bottom of the mountain will take a long time, so the convergence time will be very high. So that's a tiny step size, converges slowly. And even if you take a large step, and if it also converges, there'll be so many zigzags that even if it converges, it will take a long time. So you see that learning rate is a very important parameter. Here you see when you are far away from the minima, you take long steps so that you kind of come closer to the minima. But when you are actually at the minima, you take smaller steps, you kind of increase your brake, and then so that you can actually stop in exact place. So that is the idea here, and that is the good step size. So the step size is a very important parameter. Okay, so the step size is also called the learning rate, or eta or alpha, or different names are there. So the gradient descent equation becomes xn plus 1 equal to xn minus eta times del f of xn. So I've already said that del is the gradient, or the slope. Here it's a very important thing that we want to show, that it's actually you are reducing the value of x in such a way that you are moving in the positive direction of x, but also in the negative direction of the gradient, right? You are moving from x0, where y card is have some value where x's value is 0, and then you are moving in the positive direction of x, but you are moving in the negative direction of the gradient. Okay, so this is very important. Okay, move a positive distance in the direction of negative gradient. That's why so xn plus 1 is the new value of x, will be the old value of x minus the learning rate, or times the first order derivative of the gradient. Okay, so that means if x1's value you want to calculate, how we calculate? We calculate the value of x, the derivative at x0, and then multiply it with eta and subtract with the old value of x. Okay, from the old value of x to get the new value of x. Okay, so this will be a positive movement in the direction of negative gradient. So the starting point from where this x0, or the initial point, like here, this is the starting point, is very important, because it determines many things. I'll talk about it because it may get stuck in a local minima if you're depending on the starting value of x or x0. And also the learning rate is important, as I already said. In the default, learning rate is 0.01. So when we optimize this parameters like learning rate, starting point, this is called hyperparameter tuning, then all these things will come. What will be the good learning rate? As I already said, good learning rate is this, but bad learning rate can be too high learning rate, close to 1. So it can vary from 0 to 1. So it's a fraction, okay? So that's why it's a scaling factor also. So now I have shown an example here. So this is a univariate function, okay? F of x equal to x squared minus 4x plus 1. If it's a univariate function, it's much easier to visualize, but it's a multivariate function. There are many, many dimensions. So you cannot visualize the function very easily. So it's very difficult to think where will be the minima. So in that case, we can just focus on one part. It's like an elephant, okay? It's a big animal. We cannot see the whole thing at the same time. Then you just touch the tail or touch the feet. It's like a partial derivative. You see only that part. You think you don't see the rest of the elephant. You just consider based on that, make a decision, okay? So it's very similar to that. That's the partial derivative concept. And then here you see we have given an example. This is the univariate function. So you just take the derivative, first order derivative, not the partial derivative, and then you can get that del of fx equal to 2x minus 4. Okay, so now you see how we have shown if x0 equal to 9, that means the starting value okay, of x is 9, and the eta, which is the learning rate, is 0.1, then x1 will be x0. So from this equation you can see x0 minus learning rate times the first order derivative, which is 2x minus 4. Now x is initial value is 9, so there's 2 times 9 minus 4, it becomes 7.6. okay, similarly when you calculate x2, the x0 will be this x1, which is 7.6, and similarly when you calculate x3, this one will be the x2, which is 6.48. so you can see in that way we are moving in that direction, okay, moving in that direction, and we will have new and improved values until we reach very close to 0, and then that is the point where the you see the error is actually reducing. You can see this is x3, x0. This is basically the SSE, the sum of the squared error. This is basically reducing until you go to the minima. So here one thing I want to tell, that SSE, or the sum of squared errors, this is one of the loss function. There are many other, and gradient descent can work on them as long as if you remember, they are first order differentiation is possible at every point of the function, and if the function is convex, then gradient descent can work on all of them.